So we've looked at naming and drawing alkanes. We're now going to move on to alkenes, alkynes, and do a little bit more work looking at isomers as well. So an alkene, as we probably already know, it has at least one carbon-carbon double bond, and an alkyne, at least one triple bond in that formula or in that molecule. The general formula for alkene, CnH2n, and for an alkyne, CnH2n minus 2. So remember, for an alkane, the general formula was CnH2n plus 2. Now, the fact that we're in an alkene, we have a double bond in there, it means we're going to have less hydrogen. So for CnH2n, for instance, if we had C6, that would be H12. And if we had hexane here, C6H10, so 2n minus 2. And again, that's because the triple bond is reducing the number of hydrogens that could bond to a carbon. So they're the general formulas for an alkane, alkene, and alkyne. And you can see here's a simple example of an alkene. And we have two carbons, so it must be eth, and the suffix is -ene. And here we have two carbon, must be eth, and because we have a triple bond, it's ethyne. We're going to look at some different types of isomers now. Chain isomers we've already had a look at, and we know that due to the branching possibilities in the carbon backbone of large organic molecules, you could arrange those carbon backbones in different ways. You also remember that this only starts from butane on, or butene or butine, 1, 2, or 3 carbons in a backbone. There's no other way you can arrange those to form a chain isomer, but from butene on, you can. So chain isomers of alkanes or enes or ines, alkenes, alkynes, can contain more than one alkyl group, and sometimes they're attached to the same carbon atom, which we saw when we were naming our alkanes. So here we have hexane on the left, and here are some isomers, different ways to arrange that carbon backbone. On the left here, 2-methylpentane, that's 1, 2 carbon, 2 methyl. And here we have 1, 2, 3, 4, 5, so we're looking at pentane again, and we have one methyl group off the third carbon, so that's 3-methylpentane here. And on the right we have 2 methyl attached to the second carbon, so we have 2,2-dimethylbutane. So there are just some examples of different ways you can arrange the backbone structure of hexane. So chain isomers are just different ways of structuring that carbon backbone. Now, when we talk about a functional group, we're actually talking about atoms or groups of atoms that give that compound or that molecule its chemical characteristics. Side chains made purely of carbon and hydrogen, which we've already looked at, they're our chain isomers. They're unreactive, and they're not sites where chemical reactions occur, so they're not considered a functional group. Remember, an alkyl group is just a side chain with just carbon and hydrogen. They're fairly unreactive, so no chemical reactions take place there. But when we talk about a functional group, it's part of the compound where chemical reactions can occur, and obviously it gives it the compound characteristic chemical properties. So carbon-carbon double and triple bonds are functional groups. They're the sites where chemical reactions can occur if we break those bonds or form those bonds. Other functional groups, and before we just look at these examples here, there are quite a few different functional groups that we're going to look at later in the course, so this is not an exhaustive list. It just gives you an idea of what a functional group is and how they're different to, say, a chain isomer or an alkyl group. So let's have a look at a couple of examples here. We can see we've got a carbon backbone, and attached to it we have a double bonded oxygen. Now, if that's at the end of one of these molecules and it's capped with a hydrogen, we call that an aldehyde. And here's an example of it here. So we've got our double bonded oxygen on our last carbon, which is capped with a hydrogen, and we'd call that propanal. And don't worry too much about the naming at the moment. Again, it's something that's coming up later in the course. If we have a ketone, we've got our double bonded oxygen again here on a carbon, but this time it's kind of in the center of one of these molecules. It's not capped with a hydrogen like the aldehyde is, and for instance this one here is called propanone. Also, we could have carboxylic acid, which we know from our acetic acid. We've seen this one before, and what we'll have, our functional group, is that double bonded oxygen again on a carbon, this time capped with a hydroxyl group here, an OH, and that little H there is our acidic proton. And you can see here an example, ethanoic or acetic acid, and we have our carbon with our hydroxyl group and our double bonded oxygen. So again, a functional group is a site of reactivity in a molecule. It gives it its chemical characteristics, and it's different from a chain isomer or an alkyl group as it's reactive. It doesn't just contain carbon and hydrogen like an alkyl group does, which are unreactive and don't lend any properties to that particular molecule. If we had an organic molecule that contains functional groups, or at least one functional group, we could have what's called a position isomer. Position isomers have the same carbon chain or the same carbon backbone. They have the same functional group. The functional group, though, is attached to a different carbon, so it's in a different location. Hence, we give them the name position isomers. There's an example at the bottom that we'll look at, and we're going to look at two position isomers of butanol. It has the molecular formula C4H10O. Now, we can see here on the left, we have our hydroxyl group, this functional group, attached to carbon 1. And on the right, we have this position isomer where we've changed the position of the hydroxyl group and we've attached it to carbon 2. So like chain isomers, each position isomer is given a different name. We're not going to look at those in this lesson, but that's something that we're going to learn how to do coming up, is to name different position isomers. This lesson is just introducing you to the idea of what a position isomer is. Now at the bottom here, we could also have, we've got an example here of butene. We could have a position isomer where we've got the functional group, which is the double bond in between the first and second carbon, or we could have the position isomer where we have the double bond in between the second and third carbon. So that's also considered a position isomer of butene. One thing to keep in mind is sometimes you might be thinking that you're looking at a position isomer, but you're just looking at a molecule that's been rotated, or it's the mirror image of the same molecule. So take ethanol, for example, here. We have a hydroxyl group, OH, attached to carbon 1. And on the right, it looks like we've got a hydroxyl group attached to carbon 2. But really, these are the same molecule that's just been rotated. So remember, they're three-dimensional objects, and you've got to keep that in mind when you're looking at these molecules. Could I flip that molecule around, and that hydroxyl group, or whatever the functional group is, it's actually attached to the same carbon. I'm just looking at a mirror image of the same molecule. So bear that in mind. These are not position isomers. That's just something to keep in mind when you try to identify, draw, or name any of these position isomers. So the last type of isomer we're going to look at is a functional group isomer. Functional group isomers have the same molecular formula, but they have completely different functional groups. Now remember, a position isomer has the same molecular formula. It also has the same functional group, just located in a different position. Well, here, when you look at a functional group isomer, you've got the same molecular formula, but having a completely different functional group attached to that molecule is going to give it completely different chemical and physical characteristics. As an example, we could have C3H6O, and now we could have functional group isomers that include propanal, excuse me, which you find in smoke, or you could have propanone, which is acetone, which is a liquid solvent. So have a look down here at the structures of propanal and propanone. Propanal is what we call an aldehyde, and it has this functional group at the end of the molecule. You've got a double bonded oxygen to a carbon, and that carbon is capped with a hydrogen. Now, the same molecular formula, arranged differently, could give us a double bonded oxygen in the center of the molecule. Now, we call that a ketone, and that would give us propanone. So you can see here a functional group isomer, same molecular formula, but we have a completely different functional group, which gives these molecules completely different characteristics. Another example, C3H6O2, you could have propanoic acid, which makes your armpits smell, and we got this carboxylic acid functional group on the end. Same molecular formula, different functional group. Or you could have methyl ethanoate, which again is a solvent, and we call this an ester because we have our double bonded oxygen on a carbon attached to an oxygen, but it doesn't have that acidic hydrogen attached to it, so it's somewhere in the center of the molecule. We call that an ester. The point here, the key takeaway is a functional group isomer has the same molecular formula, but you're going to have a different functional group present in that molecule, giving it completely different chemical and physical properties. Now just contrast that with a position isomer, which has the same molecular formula, but it has the same functional group present, just located somewhere else on the carbon chain. All right, let's start naming some alkenes and alkynes. Now, the good news is the method we use for naming our alkanes, a lot of that still holds true when we're naming alkenes and alkynes. There are a couple of differences, though, that we're going to go through now. And the first difference, the big difference, is when we did our alkanes, we actually numbered the carbons to give the side chains or the alkyl groups the lowest possible number. Well, now when we look at alkenes and alkynes, the location of the double or the triple bond takes priority. So number your carbons to give the carbons involved in the double or the triple bond the lowest possible number. Disregard where the alkyl groups are. The location of the bond takes priority. We're also going to specify the location of that double or triple bond using the lowest numbered carbon atom in that particular bond. And we're going to insert this number before the suffix "-ene" or "-ine", depending on whether it's a double or a triple bond. Here's an example in the top right. There are no alkyl groups attached, so it's pretty straightforward, but we're going to number from left to right because the double bond appears between the first and second carbon. The example 2-butene on the right here, we have the double bond between the second and the third. Now, one thing to keep in mind as well is the way it's written here, 1-butene, that's from Chemistry in Focus, and you may see 1-butene, 2-butene, you may see that floating around, but it's not correct. It's not the way we're going to write it. Correct IUPAC way and the way that it's written in the HSC exam, 1-butene should be but. We have 4 carbons. We have the double bond beginning at the first carbon, and because it's a double bond, we finish it with "-ene". So that's but-1-ene. Same with 2-butene. We have but, we have 4 carbon. We have the double bond beginning at the second carbon, and because it's a double bond, it's "-ene", but-2-ene. Let's have a look at some structural and condensed structural formula in these tables. And you'll also notice there is no methane, there is no methine either. We obviously need at least 2 carbons to get a double or a triple bond between those carbons, so we don't have meth appearing here. Pretty straightforward ethene structure here, and we can see that in our condensed structural formula, which I've mentioned before. You actually do put the double or the triple bonds into the condensed structural formula. When we looked at the condensed structural formula for alkanes, we left out the single bond. So you're still leaving out single bonds, but you are including double or triple bonds when you look at your condensed structural formula here. So we can see we've included the double bond between the first and second carbon, and we have propene, obviously, 3 carbon. We don't write this as prop-1-ene. There's only one place to put that double bond, and if we rotated that molecule, it'd still be prop-1-ene, so it's just propene. But once we get up to but, there's a couple of different isomers, a couple of different position isomers we could have, so we're going to start numbering the location of these bonds. So we've already gone through this example on the top right, but looking at where this double bond occurs, I'm going to number from left to right, so that'll be carbon 1, 2, 3, and on. And the double bond begins at the first carbon. So we, as we've already done, we'd write but for 4 carbon, would specify the location of the first carbon in the double bond, and end with "-ene" because we have a double, not a triple bond. Pretty similar for our alkynes on the right over here. We are going to include triple bonds where they appear in the molecule in our condensed structural formula. And we will actually, we can call this one here but-1-ine. We have 1, 2, 3, 4 carbons, so it's but. The triple bond occurs between the first and second, so we would say but-1 and -ine being a triple bond. All right, let's go through a worked example, and then we'll jump into a couple of more examples on the next slide. So these are the steps that you'd run through to name these alkenes or alkynes. So immediately we can see we're dealing with an alkene because we have a double bond. We've got 5 carbon in total, so we know it's going to be pent. We've got a methyl group attached to the middle carbon, so that's good. We're just ticking off the structures as we go. Now we're going to number the carbons, and we're going to number from left to right, because remember, we have to give our carbons involved in the double or the triple bond the lowest possible number. If we numbered this one from right to left, then the lowest number for that carbon would be 3, which isn't going to work. So we know that the parent name then is going to be pent-2-ene. Pent because we have 5 carbon in the longest chain. 2 is the carbon with the lowest number involved in that double bond, and ene because it's a double bond. And then we can just have a look here, and this is pretty straightforward. We've got a methyl group on the third carbon, so the name for this particular molecule is 3-methyl pent-2-ene. So not too dissimilar for how we name our alkanes. There are some methods here that still hold true, but there's some slight differences. We'll jump into a couple of more examples, which is the best way to get your head around naming these alkenes and alkynes. All right. Now, you guys might want to draw these in your book, have a go at naming them if you want, and then come back and go through these answers with me, or you can work through as I go through them now. It's up to you. Okay, so the first thing I'm going to do is look for the location of the double or the triple bond. We've got a double bond in here, so it's going to be an alkene. And remember that the numbering of the carbons is based on where that bond occurs. So that takes priority over where the alkyl groups are located. So I'm going to number my carbons 1, 2, 3, and 4, and then 5 and 6, which is our longest chains. So it's going to be hexene. Then I look for my alkyl groups. I've got a meth and a meth on the 3rd and 4th. So I'm going to say that this is 3, 4, dimethyl. And we said that was hex. Yep, hex. The lowest carbon on the bond is 2, so hex 2 ene. That's a 2, not a 3. Hex 2 ene. Okay, on to number 2. Number my carbons left to right, giving the double bond carbons the lowest possible number. 1, 2, 3, 4. So it's bute. I've got a methyl group here on the 3rd, so it's going to be 3 methyl bute. And the carbon double bond here is 1, so bute 1, and it's a double ene. 3 methyl bute 1 ene. Let's go on to number 3. Number from right to left, 1, 2, 3, so it's butene again. I've got a methyl and a methyl, so I'll just draw it up here. I've got 2, 3, dimethyl, and it is butene. Yep, bute. Bond begins at the first carbon, so bute 1 ene. Lovely. 2, 3, dimethyl bute 1 ene. Number 4, I'm going to number from this side. 1, 2, 3, 4, 5, and 6. So that's hex, hexene. Methyl group on the 4th, so that's going to be 4 methyl. And what did we say it was? Hex, didn't we? Hex. Double bond begins at the second carbon, so hex 2 ene. All right, last one here. Okay, we've got an alkyne. We've got a triple bond. That's carbon 1, 2, 3, 4, 5, 6. We have a methyl group on the 3rd, so that's going to be 3, 3. Dimethyl. And we have 6, so it's going to be hex. Begins on the first carbon, the triple bond, so it's going to be hex 1 ine. So 3 more examples, and then I'm going to let you guys work on your own for a little bit. So starting with number 6, excuse me, we've got an alkene. Number our carbons, I'm going to start over here because our double appears closer to that end of the molecule, so I'm going to say that's carbon 1, 2, 3, 4. Now there's 2 ways we could go here. It's going to be hex, either way we cut it. If I label these 5 and 6, then I've got this ethyl group here, and it's exactly the same as if I had actually numbered this one here, 5 and 6, off the 4 carbon. I'd still have an ethyl group. So it doesn't really matter which one you choose here. Either way you cut it, it's going to be hex, and you're also going to have an ethyl off the 4th carbon. So this one is going to be 4 ethyl hex. Double bond starts at the second carbon. Hex 2, it's a double, so it's going to be hex 2 ene. 4 ethyl hex 2 ene. Number 7, let's have a look here. Carbon 1, 2, 3, 4, 5, and it doesn't matter which one we number as our 6th carbon because we're going to have a methyl group or 2 methyl groups off that 5th carbon, so I'll just make this one the 6th. There we go. Now we've got 5, 5, 5, 5, dimethyl, hex, double bond starts at the second, so hex 2, it is a double, so it's hex 2-ene. 5,5 dimethyl hex 2-ene. So we've got two methyl groups here attached to the fifth carbon. Okay, let's have a look at number 8. Interesting. So we could go 1, 2, or we could go... So this could be numbered from either direction. It could be 1, 2, 3. And if we came the other way, we'd still be we'd go 1, 2. So either way we number this from left to right, it's going to be meth, eth, prop, but 2-ene. But because we've got this alkyl group, we've got meth on this side here. We're actually going to use numbering from left to right because that'll also give us the lowest possible number for our methyl group. So that's kind of a tiebreaker. If we could go from either direction and the lowest carbon with the double bonds is going to be 2 from either direction, whether we go in that direction numbering carbons or this direction numbering carbons, use the location of the methyl group here in this case as the tiebreaker. So in this case we're going to have 2 methyl, what did we say, bute, 1, 2, 3, 4, bute. Double bond starts at the second, so it's 2, it's a double bond, ene. Now, if these ones on this page, they're all alkenes, the only thing that would be different if it was an alkyne was this would be a triple bond, for instance, or this would be a triple bond for number 7, and it would just be 5,5 dimethyl hex 2-ine. That's the only difference there. So if you can name these alkenes, then the only difference if they were alkynes is you would finish these names with ine rather than ene. So that's pretty straightforward. So that's naming alkanes and alkenes. What I'd like you guys to do now is you've got some questions here and the answers are on the next slide of this PowerPoint. I'll get you guys to work through that, then check your answers. Good luck and let me know if you have any questions. All right.